So here's a quick note on the Faraday's law. The form that I gave you so far was that the EMF is equal to minus n. N is there if you have, well, n is there. That's just the number of loops you have. Times the change of the magnetic flux with respect to time. Now, it should be pretty obvious that the more adequate equation is the one that includes the derivative, and so you'd have d of the magnetic flux dt. But because this expression for the magnetic flux can have multiple variables in it, it's actually the proper way. It's actually to use a partial derivative, so that you have minus n times partial of the magnetic flux with respect to time. All right, so there's that, and then suppose that so this would be more accurate, more correct expression for the Faraday's law. So I'm going to put here, this is a Faraday's law. Faraday's law. And let's do a simple problem. And so what we're going to look at is a case where, let's look at a simple one. Simple problem. Let's say that the flux, magnetic flux through a loop varies as a function of time, and it's some sort of a cosine function. So let's say it's 5 Webers times the cosine of 3 pi t. Let's just make it 3t, cosine of 3t. So the flux through a loop varies at this rate, and so I have some kind of a loop here. Maybe this is the loop that I have, and then there's a magnetic field that points through this loop, so there's a magnetic field that points inside B, and somehow the flux of this magnetic field B varies with time. So the question is, what is find the expression for the EMF induced in this loop? Well, n is 1, since I drew one loop, and so what I would get is that EMF is equal to minus 1 times, and then you take the partial. There's really actually no need for a partial given the equation that I provided you here, but anyways, times 5 cosine of 3t. And so you take the derivative of this expression, and that would be 5 comes out, so negative 5 times derivative of the cosine is a sine, but it's with a negative, so it'd be minus sine of 5. I'm sorry, sine of 3t, and then all of this times 3. In other words, what I get is that negatives nicely cancel out, so I have 15 times the sine of 3t. And so if you were to graph this thing, what you would end up with is function of time. You'd have voltage or EMF here that you start at 0, and then well, it's just a sine function, so you run like this. And maximum voltage you would have is 15 volts, right? That here, that's the maximum, 15 volts. And this thing goes back and forth, back and forth, back and forth, and you could figure out the frequency if you wanted to. But there's that. All right, and then let's turn this Faraday's law into Maxwell's equation that is typically stated. So what we have is that the EMF is equal to minus, we'll forget n for the moment, we'll just simplify it a little, so we'll write d phi dt, where this is the magnetic flux, and so magnetic flux is defined as E dot A, where you integrate over some surface. Right? How much of the magnetic field is pointing through a specific surface. And so specifically here in these problems where we generate electricity, we're looking at the cases where you have a loop, closed loop. This is not a closed surface, this is just a closed loop. This is an open loop, in case you're wondering. Right, this is an open loop. But this would be a closed loop. So I have this loop, and then I have a magnetic field that points through it. So there's so there's that loop, and then the magnetic field points through this thing. Here's magnetic field B. if the flux of this magnetic field B is changing, then I'm going to end up with some current flowing, and the current could flow either clockwise or counterclockwise depending on how the flux is changing. But anyways, let's just say that I comes out to I points like this. Exactly how do you determine the direction of the current I? That's yet to come, but for the moment, let's say that there is a changing flux and therefore we get some current here. Well, that's kind of equivalent conceptually to some extent to the following circuit. You could redraw it like an electrical circuit where you have, if you have a current, then there's got to be something pushing the charges, and that would be the EMF, or I told you to think of this as voltage. So you could redraw this circuit to be equivalent to sort of having a battery where you have this voltage that is your EMF, and then you have this loop that goes around. There's a certain resistance of that loop, and then this thing comes back, and so you have a current. You have a current I here that flows the resistor R. Now this EMF here, so this EMF, actually let's just write it in red. So this EMF, there's an equation for it. It's the equation for voltage, which is E that L. And you might wonder where's the electric coming in? Well, the EMF, you might recall that E electric field is delta V, was delta V over delta D. This is really the equation that we used most often, but you can turn this into E that DL equals delta V, and that's delta V is just EMF. So there's a subtle difference though between EMF and actual voltage, but what I want you to think of is the electric field that shows up here. So suppose that you have the changing magnetic field. I'm going to write this out in black down here. Suppose you have a changing magnetic field such that you end up with changing flux. Changing magnetic field is going to give us some changing flux. And then this changing flux is going to generate current, I. But if you have a current I, then what that means is that you have a bunch of charges here that are pushed with some force F and they flow. So you have a bunch of charges here and these charges are pushed with force F and they flow. But if you have charges that are pushed with force F, then you have to have an electric field, right? Because Q times E equals F. So if you have a charge and there is a force on the charge, then there's an electric field. And the electric field points in the direction in which the charge moves. And so we would have here electric field that would do something like this. We would have electric field everywhere along this wire. In fact, the electric field will also be present in space around it. But anyway, so there's the electric field here. Perhaps for the first time you see that changing magnetic field gives rise to an electric field. There's an electric field that is present, and so this is the electric field that shows up in this equation here. All right, if it made sense, great. If it didn't, then I guess it didn't. But what we'll do now is we're going to take all of this and this, combine it into one expression, and so what we have is EMF is the integral EL. But we want to integrate here along that closed loop. So I'm going to put, if I wanted, well, along the surface, not the surface, along the loop. So maybe S is not quite right what I want to put. Yeah, I mean, all right, anyways, equals, and then on the other side, I'm going to have negative here, and then there's a partial ddt, and then I have B dotted with A, where this is the integral over the surface. So then you're calculating the magnetic flux through the surface S, and that's that. And then here you integrate electric field along the edge of that surface. So I guess I'll put S here, but just remember that this is the edge. You integrate along the edge of surface S, and here you integrate over the surface S, over the surface. There's a difference. This is dA, this is dL. Here you integrate along the edge, you add up all of these little dLs, and here you have all the little dAs, and so you take dA, 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 and you sort of add all of these little segments of the area up. There's a difference there. And actually, interestingly enough, as you do these circles here, you can see how these, perhaps you can see how they curve. You can almost start guessing where this thing is going. That's a bit of a stretch, but you can see how the DLs here, they can point in the same direction in which I can curl these little circles, and without too much, well, perhaps I'll skip a few steps, but you can take this expression, which this, by the way, is the this is the Faraday's law. This is how the Faraday's law is frequently stated when Maxwell's equations are given. This is in the Maxwell's equations. You can take this and you can rewrite it in a vector form, in a derivative form, in the following way. Curl of E equals minus dB dt. But you're not responsible for this equation, so this is sort of in parentheses. And as a side note, you need to be aware of this equation, and I think we may solve a problem or two somewhere at some point with it. All right,